Inviting me. All right. Thank you very much for inviting me to present this work that we're doing in my group with deep learning. I first wanted to actually introduce a little bit of some recent highlights of the work that the group is doing so that I put what I'm going to talk about here in context. And so, oops. Here we go. So our work focuses on understanding the dynamics of past, present, and future climates and how it impacts weather risk. And so some of the recent work that we have put out is studying the exposure to humid heat of human populations and also critical infrastructure. The work that I will talk about today about reconstructing atmospheric blocking using deep learning methods. We have another preprint out that may be of interest to you. We use deep learning coupled climate emulators, so coupled atmosphere-ocean models to look at the impacts of, say, the tropical Pacific to atmospheric circulation. We do that for pacemaker experiments, and then machine learning simulations and predictions of El Nino. This is something that Gerardo Rivera-Tello, who is a fellow here at HITSI, is leading. So he had a workshop a couple of weeks ago, and I'm sure you've heard quite a bit about this. All right, and so we're talking about weather risk, right? And weather risk is particularly important when you have events that persist and therefore their impacts persist. So this is some examples of the events that are of interest to us. At the top left there, you have the 2021 Pacific Northwest heat wave that you may remember, and a lot of days of significantly high temperatures, 116 degrees Fahrenheit in Portland, for example. Earlier the same year, 2021, in February, we had the Great Texas Freeze, or otherwise known as the Valentine's Weekend cold outbreak in Texas, that also made a lot of headlines. Earlier, Hurricane Harvey, again, made landfall in Houston, and what was significantly the impact of that hurricane was not that much, wind and the things that you typically think about when you think about hurricanes, but it was rain. So it dumped more than 50 inches of rain in a matter of a couple of days, and you can see all the flooding there. And about 20 years ago, well, almost exactly 20 years ago today, some of you may know or may have heard of or may remember. I was not here, so I've heard about this. A prolonged period of rain, 40 days of rain in Hawaii, it was that caused significant flooding, and it's an event that a lot of people still talk about. And so all of these events are very different, right? You have heat waves, you have cold, you have flooding, you have rain, but they all have a common feature. And the common feature here is stalled synoptic flow. So as I say there at the title, when the weather stops moving, the impacts compound. So what is common here is that the systems that created that weather were not moving along as you typically would have them moving along, the northern hemisphere or the southern hemisphere, right? So let's see what happened in each one of these cases. The Pacific Northwest heat wave, the primary driver for that was a persistent, exceptionally strong reach of high pressure. And this is what you see here in this plot. This is indicative of high pressure that stayed over a long period. And right where this high pressure system, this is shown here as the anomaly of the geopotential height, right where that high pressure system was stalled, you see you have all these high temperatures. And that, of course, caused deaths, hospitalizations, wildfires in Canada, agricultural and ecosystem damage. Now, earlier, as I said, the same year, you had the Texas freeze, and that was again associated with a high pressure system that what it did is that it disrupted the flow here of the jet stream, and that made the jet stream kind of meandering like this. That allows this cold Arctic air to move south, and this is what happened, and you had all of this snowfall there. What was important about this period in Texas, of course, and what made headlines was that the power grid collapsed, right? And that was what created most of the impacts. Now, Hurricane Harvey, it's a hurricane, right? But why didn't that dump so much rain over, a few days? Because what normally happens is that you have a hurricane making landfall, as you see here, and then it will move inland and just dump its moisture as it goes along and dissipates as a system. But there was this high pressure system sitting up there that you see in this plot, and that stopped the hurricane from moving, and that is what this blocking high pressure system, that is what created that prolonged period of rain that flooded Houston. All right, so 20 years ago, the rainfall in Hawaii was again associated with a high pressure system that stalled. This is what you see here. This is a dipole. There's high pressure in the north of Hawaii and a low pressure south, kind of in west of Hawaii. And this dipole structure is called a Rex block. And it stayed there for quite a long time. So we had rain from February. It's not 40 days, but it's known as 40 days of rain. But from February 19th to April 2nd, there were 111 flash flood warnings. Typically, you would think you have about 10 a year, not 111 in a few days. And one tornado, a lot of flood events there. Okay, so as I said, now all of these events are associated with atmospheric blocking. So there's high pressure systems that they come in somewhat different configurations, but they all remain stationary for multiple days to multiple weeks. So the Pacific Northeast heat wave was associated with what we call an omega block. It looks like this. It looks like a capital Greek letter omega. So you have high pressure and then low pressure in the flanks there. And the Rex block that I mentioned for Hawaii was this dipole pattern. So depending, and you can see something similar impacts for an omega block over Europe. So depending on where you are, you can have mild weather, or you can have heat wave, or you can have heavy precipitation, snowstorms, thunderstorms, and all of these things. So these are the events that we're interested in, and generally they're rare. They're consequential, and partly they're consequential because they're rare, right? So it's not something that you have, every day and you are prepared for. So what this plot here shows you is how rare they are, right? So it shows you the frequency of days in each one of the 4 seasons for the Northern Hemisphere: December, January, February, March, April, May, June, July, August, and September, October, November. The colors here are the frequency, so the percentage of days in each one of these seasons that belongs to a block, right? So what you see is that, okay, maybe you go to 14%, 16%, right? That's not a lot. But because it persists, the impacts scale non-linearly with the duration of these events. So, okay, they're rare, and because they're rare, it means that we don't have a lot of these events to go off on to understand their dynamics and be able to better predict them and characterize them, right? The other thing that happens with this frequency is that low frequency, but still it is modulated by other things that's happening around us. For example, the tropical Pacific. So this is a lot of the work that we're doing in the group. Frequency that I just talked about, it can be different depending on whether, for example, you have a La Nina event or an El Nino event. So the background here, the contours are what I just showed you for winter. That's the frequency averaged over the whole period that we have it. And now the colors are what happens during an El Nino or a La Nina event. So during La Nina, you can see you have more. This is the difference down here. So you have more blocking, or you have a higher chance of having these blocking events forming. During El Nino, you have less. But this also is modulated by something else that happens in the background, which may be happening at decadal timescales. So depending on whether you have warmer or colder Pacific in general, that may come in the form of what we call the Pacific decadal oscillation, these frequencies also can change. Also, whether you have an Eastern Pacific or a Central Pacific El Nino event, you can again have these difference plots look quite differently, all right? So back to these events that I talked about, as a matter of fact, both the 2021 and the 2017 events, they were happening during a La Nina event. So I just showed you that during La Nina events, you have higher frequency of these events, and this fits what we have seen also for these consequential events, right? So we have these rare events, they're consequential. If we misrepresent them, we misrepresent the risk that is associated with this. Okay, is there something up with my, is it? Oh no. Okay. So let's look at the dynamical climate models that we use to understand, how these things form and maybe how they may change in the future. This is again for December, January, February, the frequency that I showed you. This is the frequency that the models are simulating, and this is the difference. So you can see there are biases, and for something that has a 14% frequency, if your bias is 4 or 6%, that's quite a bit of a bias, right? And so we do know that models have climatological biases, and they also have biases in simulating isoactivity, and that means that it affects how they simulate these blocking events. And of course, what in many cases we're interested in is that, well, what should we be preparing for in the future? So how would these events maybe change? And so we look to these models to tell us that. And what they tell us is many different stories. So what I show you here at the top is for winter. This is the change in frequency in a future climate scenario versus a present day climate scenario. At the bottom is the summer. What each one of these columns is a different way of detecting these events in your climate output fields, right? So immediately you can see that depending on what method you're using, then you can have different events. And there's a good reason why we have all these different methods that disagree with each other. Because these events are rare, as I just mentioned, there's not much to go on to really pick out one method that, okay, this is it, right? Because every time we have one of these events, something different may happen. The 2021 Pacific Northwest heat wave is touted as unprecedented because we haven't seen something like this before in the record, right? So that means we have uncertainties based due to our lack or limited theoretical understanding and kind of lack of consensus in how we track these events. But also, if you look at the stippling here in these plots, the stippling shows you the areas where the models, different models, you have 10, 20, 50 models, disagree with each other. So there's quite a bit of stippling there. So there's a lot of disagreement now across models for using the same method, right, to detect these events. And if there's anything in terms of agreement, you see you don't really have stippling in a lot of areas that are blue, right? So what does that mean? A decrease in blocking in the future. A lot of that consensus in the models, it stems from the fact that they generally simulate enhanced tropical warming, and so an El Nino-like change in the tropical Pacific. So as I told you before, when you have El Nino conditions, you have less blocking. So that's why they agree. But in our community, there is a lot of spread in how these models are simulating tropical Pacific change in the future, and there's a lot of debate about whether they are biased or not in terms of these projections. So the bottom line of all of this long introduction that I gave you is that there's a wide range of prolonged weather extremes, be it heat waves, cold spells, floods, that are associated with atmospheric blocking. It is a rare phenomenon. It has strong variability at multiple time scales, year to year, decadal, and it depends on what's happening quite a bit in the tropical Pacific and in other oceans. And what we understand about blocking and how it may change in the future is challenged by the fact that we have a short instrumental record length, right? So if we have a good instrumental data from the last 70 years, that's 70 summers. Well, that's not enough. In 70 summers, 10% is blocked, right? So you understand that we have a sample size problem, okay? And models, the dynamical models that are solving the equations of motion in the atmosphere and the ocean, they have to struggle with simulating block strength and duration, and the short record doesn't suffice us to constrain these uncertainties. We cannot say, well, this model is good, the other one is better, because the record is not long enough. So we have this problem, and typically when we have a problem with data, the only thing better than data is more data. But as I'm sure all of you agree here, they need to be also better data. But unfortunately, in our line of work, you don't always have better data. Now, we can't constrain what the models are saying or understand things better for the future because we don't have data from the future. The future hasn't happened yet. When it comes to climate and weather, we only have one realization of, what happened between the 50s and today, that we have good instrumental data. So the only way to extend this length of the record, you can do bootstrapping, right? We do this all the time. To do statistical significance with a shorter record, you do bootstrapping. But that's not a different realization of what happened. It's a smart technique to get statistical significance. But it is, again, you're pulling yourself from your bootstraps. So the only thing we can do is try to extend this record to the past, right? So this is where paleoclimate comes in the study of paleoclimatology. So what do we mean with paleoclimate? What type of records are we talking about? The records are cave records, coral records, sediment cores, ice cores, tree rings, ocean lake sediment cores, as I said. So all of these, how does this work? All of these different, you have your environment, and there's a sensor in your environment that senses what's happening, right? And then it records it in an archive, and there is some variable in that archive that gives you information about your environment. This is kind of the conceptual model of this proxy system. Right? So think about corals. What is the environment that corals live in? The ocean. And what is important in the ocean? Salinity and temperature, as far as how a coral grows. The sensor is the coral, and the archive is the coral skeleton. So the observation, what you actually measure in the coral skeleton, is the ratio of light to heavy oxygen isotopes. And that gives you some information back about your environment. Then you can use a transfer function by having this ratio of light to heavy oxygen to reconstruct what was temperature, what was salinity. Similarly with the trees, right? The trees, what is the environment? Is where you are in a specific location. The sensor is the tree. The archive is the trunk of the tree and how it grows, because how fast your tree grows depends on whether you have favorable temperature and precipitation conditions, right? And so the observation is, in some cases, and in most cases, the width of the tree ring. The wider it is, from that you get information about temperature and precipitation, okay? So, all right, you have information about temperature and precipitation, so maybe you can say something about what was happening with atmospheric blocking. So there's a few studies that actually do not reconstruct atmospheric blocking per se, but used tree rings or other lake sediment cores, etc., to infer some variable that eventually down the road is connected with atmospheric blocking. So there's one study, they were looking at mega droughts using tree rings, and then they connected that with the location of the jet stream, and not presumably, but in reality, where the jet stream is associated with frequency of blocking. So they did some inference like this, that it looks like there have been increases in blocking activity and persistence when you had these long periods of drought in Europe. Another study looked at, again through this inference process and a transfer function, really, they simulated, or they reconstructed geopotential height, which is your pressure in your atmosphere, and again said, well, maybe in the 1400s there was a reduction in blocking. But the problem that we have here with all of this is, first of all, a temporal resolution problem. You have tree rings that, what do they represent? The growing season, right? So this is the summer in the northern hemisphere, or in the southern hemisphere too. So summer, May, June, July, August, right? This is when the trees grow, and you have a seasonal signal, right, in those trees. But your atmospheric blocking is a synoptic phenomenon. It's something that lasts for a few days, right? So you have a temporal resolution problem first. So sometimes you can reconstruct, your geopotential height. So what was the pressure like? But that doesn't necessarily mean that it tells you something about what your blocking was or your blocking frequency, because we're operating here at different time scales. The other problem we have is that if you have tree rings, for example, that reconstruct temperature, that's what the tree feels, temperature. There's not a known transfer function, or if you like, a relationship between, okay, this is temperature, then this is blocking. This is something that actually we don't know, and it's actively being researched, right? What is exactly that relationship? So it's not that you can just use an equation and say, okay, now here's the blocking. So we have these problems, but the desire is still to be able to get information about past blocking frequency using these paleoclimate archives. And so what I did here in this work that I'm presenting today, finally we got to the deep learning, thank you for your patience, is I said, okay, we don't know the relationship between temperature and blocking. It's a very complex relationship, but we definitely can use a deep learning model that doesn't really need to know the relationship, but it can infer it. So what I did here is I used the UNet. So this is it takes an image in and gives you an image out. And what this model takes as input is May, June, July, August surface temperature anomaly. This is so how much warmer or colder you were in its location where your trees were going, and it goes through the motions here. This is regression-based functions, right? Because we need an unbounded result, and you transfer some information from previous steps and some nonlinearity using the skip functions, and then what you end up getting on the other side is the June, July, August blocking frequency. So this is now the percentage of days that belong to a block in your that is consistent with what your temperature anomaly was. Okay, so this is input, this is output. So that's my desire, and I have to train this model somehow. And we just talked about how we don't have data. And so how do I train this? This you may have heard before if you've listened to talks that from the side of climate science using deep learning models, that typically you would use climate model simulations now that you have many years of data as your training data set. I also used whenever you see error 5, this is reanalysis, so we will call these our observations, but that's only 50 years of data. So primarily, the model is trained on climate model output data. From the climate models, you have temperature, you can calculate blocking frequency, you get your training data set. So I used 19,048 years. This is my training data set, and this is what this looks like. This is the frequency for June, July, August, blocking frequency from these models, right? So on average, it looks like this. This is what it looks like in observations. I talked before about biases, right? So you can immediately see some biases, and I'll come back to that. But this is a drop in the bucket, so in the training data set. So primarily, you're just trained to do this. So then in our test data set, you see that there is this is a test data set. This is on average what the model that I call PaleoBlockNet did. And you see they're very close to each other. My test data set has 1,414 years, and the median pattern correlation now, so every year, how well did you do in getting that pattern, is about 0.8, which is pretty good, I would say. So now I have a model that can get temperature anomaly as input and give me blocking frequency as output. So let's go and try to get that information now from the past. So as input now, we're going to use in this model that is trained, we're going to use a paleoclimate reconstruction of temperature anomaly, right? So what is this paleoclimate reconstruction? It's based on tree rings. And that's why I talked quite a bit about tree rings so far. So this is the network of where these tree ring records are. And what King and Al did here is that what we call paleoclimate data assimilation. And so this is based on, it's a hybrid between climate model output and the temperature, the climate records. In simple terms, it's not very simple, but you find the patterns of gridded data, right, that best match what you actually have at all these points from your tree ring records. And this is what you see here on the right. How well does this temperature data set match that period that overlaps with observations, right? So this is correlation. So as you can see, you can go all the way up to 0.8 or 0.75, something like that, which is very good for, remember now you're looking at the width of a tree ring and trying to get temperature from that. So that's not that's a tall order, and it's actually a very good reconstruction. And as you can see, and we'll come back to this, the reconstruction is better where you're better constrained by data. Where you have more data, you are able to reconstruct the temperature better. So this is over the period 1900 to 1988, where you have some instrumental data to make this comparison, but the actual gridded data set you produced spans 750 to 2011, right? So it's a last millennium data set. So this is what now I'm taking. It's a gridded data set, much like how I trained the PaleoBlockNet, right? And this is what I give as input. This is one example. This is the input that goes in from this data set, and that's the output that comes out, right? And so by doing this, obviously you give the time series, you have 700 how many years, 1400, something like that. And then on average in this period from 750 to 2011, this is the reconstructed blocking frequency that you get. And so what is worth noting here is, first of all, you have a separation of the main activity blocks of blocking, right? Where do you have blocking? You have in the Pacific, you have in the Greenland area, in the Atlantic Ocean, and then you have over the Urals. These are kind of the main blocking frequency, and you can see them separated, even though you see there's a lot of smoothness. This smoothness comes from how your temperature data set is. When you're doing these paleoclimate reconstructions, you have inevitably, where you're not very well constrained, you have quite a smooth surface, and this is what shows up in this reconstruction as well. Nevertheless, you capture the main blocking activity centers, and then how well separated these centers is depends on the model used for the temperature reconstruction. So remember what I said for this temperature reconstruction is that it's a combination of the tree ring records and climate model output. So you don't just use one model, you use a bunch of models. So you actually have, this is an ensemble, that's why I say down there ensemble mean, right? So this is an ensemble mean from all these different versions of this reconstruction based on what your prior distribution is from the climate models, okay? So what is an important thing to notice here is that, and I found that very actually insightful, that remember this PaleoBlockNet was actually pretty much trained on this. And as you can see, the separation of the Pacific blocking here, this center, is not actually, it's not really separated in the way that it is in observations, right? But then when I give to this model the temperature reconstruction, that is observations, the best we can get with the tree rings, you get a better separation here of this. So you have the extent of this looks like the extent that you have in the kind of the higher fidelity era 5 data set. So what does this mean to me is that the climate models, they actually simulate the correct relationship between surface temperature and blocking. We don't necessarily know all the details of that relationship, but they must be doing it right, because then this is where the PaleoBlockNet is learning from. So then when it goes and takes as input something that is supposed to look like observations, then it gives you something that actually looks like observations better than the models. And so that means that these biases in the models, they may be stemming from temperature simulation biases or a chicken and egg situation, but not that the climate models are not getting the relationship right, because if they weren't getting the relationship right, then PaleoBlockNet also wouldn't get the relationship right, because it's trained with them. Okay, so this is one thing. All right, the other thing though is I just said, well, but when you give to this model input, that input is a hybrid product of the actual record, which is the tree ring, and climate model output. So how do we know that this reconstruction is actually constrained by the paleoclimate data? Because that's all we're trying to do, right? Give information about blocking in the last millennium that is constrained and is consistent with what the tree rings are telling us. So we need to prove that, right? Is it actually learning, or is it just, doing whatever it's doing based on the climate model, the background climate model kind of information, and not the tree rings? So how do we go about showing this? This is the what I showed you before, but with the different data set. But this is how good your input is, right? This is the correlation between your temperature reconstruction and your observational kind of temperature anomaly. Again, you see the same thing as before. You have better skill where you are better constrained by the data. This is over this overlapping period, the correlation between what PaleoBlockNet tells you is the blocking frequency and what was actually the blocking frequency. As you can see, obviously you need to look at where you actually have blocking, not to areas where you don't have blocking. And it's actually pretty good. And remember, the statistic that comes out of this is that 0.8 correlation coefficient, right? So you're good there in terms of the output. But then you ask the model, where were you more sensitive to the input, right? And you can do that by using, say, integrated gradients. This is an explainable AI method, right? So what you do is that you perturb the input little by little, and then you look at what's the difference in the output, so for blocking. So it tells you how sensitive you are to perturbations of the input, or in other words, where did you actually pay more attention to make your inference. And integrated gradients by construction, they are, because you do small perturbations on the grid cells, they are quite noisy, and that's what you see there. But you still can tell that you have stronger gradients where you have your data. So what does that say? That the model actually was looking at where it's better, the input is better constrained by the data to make its inference. So it is constrained by the input data from locations that are well constrained by proxies, even though PaleoBlockNet, the deep learning model, has no idea where the records are, right? It doesn't know these dots that I have put here, but it still pays attention there. My explanation about why this is happening is because, remember when I told you how do you make this reconstruction? You have higher variance in your figure where you're better constrained by the data. You have more information, and elsewhere it's a little bit more smooth. So the interesting things in your input data are happening where you actually have the proxy data. So it makes sense to me that, in the end, your model, PaleoBlockNet, will look at where there's something interesting happening. So by construction, if you like, or you are actually being constrained by the data. Another way to show that is if you say, okay, what if I don't give to the model the input data set that is a temperature reconstruction constrained by the paleo data? What if I give to it just model output? Model output is not constrained by any observations. It's just the model runs and it gives you temperature, right? So what happens then? So here's what happens. When I give model output as input, the temperature anomaly in the model doesn't have any correlation with the actual observed temperature anomaly, because if anyone here has taken my class, you know that these model runs, they don't have a calendar. So then they produce their internal variability, so their temperature fluctuations that don't have anything to do with actually what was observed. It's not we're not doing a reconstruction of what happened. We have a model, climate model, a free run, right? So there shouldn't be a correlation between the temperature that the model gives you and the temperature, that you have in observations. And so this is what you see here. So as you should also expect, paleoblocknet's inference of blocking also shouldn't have any correlation with what actually happened, because it just got a random variability, a random temperature, and it gave you random. Still, remember the statistics for how well this is, though, in terms for how good this is when you actually give to it observed data, not climate model, is the 0.8, right? So, and then we do again the same exercise with the integrated gradients. Like where are you more sensitive to perturbations? And what you see is nowhere, right? Everywhere is the same. So then this again supports the argument that before, when we're actually doing the reconstruction, we actually are constrained by information contained in the paleoclimate data. Otherwise, we wouldn't be doing this. It would be a random reconstruction, like it is if you just give to it like a random model run, okay? So having this, how am I with time? Okay, I'm good. So having now this reconstruction that we like and we kind of believe, we can look at time series of blocking activity in all those different centers that I talked about. So this is what you see here, and now going kind of to the science of what we're hoping to get out of this, right? Is we see if we do change point detection analysis, this is what these different shading regions say. They tell you where do you have statistically significant change in your blocking frequency, and you can see that in most of these locations it kind of coincides with the periods that we call the medieval climate anomaly, when it was warmer, and the little ice age when it was colder. And so we get some real information that we can then connect to the mechanisms of atmospheric circulation during these periods. Those periods were likely primarily forced by solar forcing and volcanic forcing. So the other thing I want to point out in this is the green lines here is actually the observed. This is the period where we have overlapping, right? And what you can see is that from the reconstruction to the observed, you have a step change. So you overestimate blocking, but you get the variability right, which is what interests us. And it's not surprising that you have this step kind of overestimation or underestimation, because as with all models, what you put in characterizes what you put out. So what the reconstruction got as input was that temperature anomaly. I showed you the correlation with observations, right? It's not perfect. And so you would expect that the output is not going to match exactly what your observed blocking is. But when you give to the model the corresponding observations now, not the reconstructed, that's the blue line, and it matches pretty well. Not everywhere, again, in the North Pacific there's a little bit of a step again, but if you see in the other regions, the blue and the green line are actually pretty good. So the reason for the bias here is the input, it's not the model. That's where I'm getting at with this, right? Okay, so, and from all of this, we were able to go back to our original questions in terms of atmospheric science, right? Of what is important for all these changes in blocking. And we were able to connect it with tropical Pacific climate variability. This shows you how El Nino or La Nina, like your tropical this time series, shows you the gradient of temperature between the east and west of the Pacific. And for example, what this says is that, well, in the periods where you have decreased blocking, you have this El Nino-like mean state in the tropical Pacific. And also what it says is that if you actually do frequency analysis on this, you'll see that the frequencies that are associated with this variability at the El Nino timescales, they're also more significant in this period. So you have more of an impact of the tropical Pacific. And so these are the things that, you know, in the end, while we're doing all of this, in order to be able to understand better the relationship between, say, El Nino or the tropical Pacific and atmospheric blocking. And we can do that by having this really long time series. And the point here is, I'm not going to say too much on this, but the point here is that you can explain, depending on the changes on the gradient, you can explain the patterns as well, not just the time series, right, mean change, but also the patterns that are different between these different periods where the tropical Pacific is different. So I'm gonna finish here. This study that I just presented was the first deep learning reconstruction of a synoptic scale phenomenon from low resolution paleoclimate proxies. I kind of dare to say that the temporal downscaling problem for proxies, it has been a problem for a very long time, and and very many sophisticated methods are being used for this. But this deep learning gives us one additional method where you don't really know the relationship. Maybe you don't really need to know it, but you can still have a very skillful reconstruction. And then using that reconstruction, you can actually answer questions like the big questions that I just talked about. What is the relation with the tropical Pacific? What may happen in the future? So this is a method that can be used for extracting paleoclimate signals with unknown and complex relationship with the variables that actually are being reconstructed. The tree ring, as I said, it feels the temperature, right? These are you have a limited number of variables that are directly being reconstructed by these data sets. I also hope I convinced you that the deep learning model the inference is constrained by the paleo records, because otherwise this would be useless, right? You're not doing a reconstruction if you actually don't show that you are constrained and you do incorporate information from the paleoclimate records. And why? First of all, okay, that is good for all the reasons that I mentioned, but there's also other ways that this is important. You can have an investigation of the effects of expanding or contracting where you go and get data from, right? Your networks. You probably are thinking, as I'm thinking, you can do ablation studies, right? You can say, okay, so what if I actually don't have these tree rings from this location? What happens to my reconstruction accuracy? Or maybe if I have tree rings there, or any other paleoclimate proxy, this is generalizable, right? Any other proxy, where should I go and get data from that actually are going to improve my reconstruction the most? Because, all of these, this is not just the only consideration, of course, for going and getting paleoclimate data. There's a lot that goes into these expeditions, and often they're very, very expensive, right? If you think about ocean sediment coring that a lot of our colleagues here are doing at UH, you go with a research vessel that is very expensive to run in the middle of nowhere and coring records, right? So you can use this type of techniques to guide and design your expeditions in some sense, given all the other constraints you have, obviously, right? The other thing is, this is an adaptable, this is very simple what I did, right? It's a U-net with regression, that's nothing too fancy about it. But what can you do? You can extend this, you can put attention mechanisms in it, you can do regional weighting. I showed you that by construction it ended up that it really focused on the locations that are better constrained. But you can also build that in how you build it. You build the model. You can say, I want you to pay more attention to this or pay more attention to that. You can change your loss functions and have them be physics informed, right? And so there's a lot of things that you can do to really make this as complicated or as simple as you want to make it, and get results that actually lead you to get insights about the dynamical insights, which is the last point that I'm making here, is that in the end, what did this enable us to do is to really constrain that relationship between climate in the tropical Pacific and atmospheric blocking. And this is important because remember, when I started this whole talk, I was saying that, well, the reason why we believe we're going to have less blocking in the future is because the models say this is what's going to happen in the tropical Pacific. So you start being able to understand better what is the impact of this type of model biases, if they exist, or model uncertainty, right, for blocking projections. And so I'm going to end here. That's the paper there. And with the help of Charlie Robinson, who was an undergraduate student here at the Computer Science Department, and Gerardo Rivera-Tello, there is a website as well that you can go and you can kind of play around with this, get time series, look at the animation, and the long-standing thing here is because it's running the model in the back end. We're going to add the capability of user input to upload your own data set to do this. We We did some user input in the other work that Gerardo has mentioned, and then we got attacked by bots, and so we're kind of. I think we need to make sure our cybersecurity is all good before we enable that, but that will be coming in the future. That's it. Thank you very much for your attention.